Hi all, welcome to Deep Learning. Welcome to Deep Learning by First Principle series. Okay, in this video we are going to see network representations and notation. Okay, how do we represent a network and its notations? Okay, so first we will see. Yeah, how to. First we will go step by step. First we will see input, then we will see weights. Okay, then we will see transfer function and activation function. Finally we will represent our output. Okay, our output. So usually the inputs are represented by x. Most of the papers and most of the literatures, inputs are represented by x and outputs are represented by y. Okay, so and if you have n number of inputs, it's represented as a x1, x2, x3 as the n. Okay, so these are represented as a subscript. Okay, subscript. Okay, and then we will see next we will see the weights. Okay, weights are represented by subscript and a superscript. Okay, subscripts have a two parts. Okay, subscripts have a two part w11. So this number is okay where it is starts. Okay, where it is starts. st which neurons it starts. Okay, which neurons it starts its previous layer. Okay, its previous layers neurons where it starts. this is the current layers. Okay, this is the current layer neurons where it ends. Okay, this is where it starts. Okay, here where it ends. Okay, and like that here we can see. So okay, here this is the previous layer. It starts in previous layer and it ends in current layer. Current layer. Okay, so this is the 2. Okay, this is the 2 and this is the same 2 2. Okay, so this is the 1 2. This is previous layer. It starts from the previous layer second neuron. It starts from the previous layer second neuron and it ends in the current neuron, current in the current layer. So sorry, in the current layers first neuron. Okay, so these are the representation of the weights, and superscript is the where it okay where it belongs to, which layer it belongs to. Okay, this is the superscript represents. Okay, this way weights are represented. Next we will see the transfer function. Okay, transfer function is as a one subscript one superscript. Okay, subscript represent the which neuron numbers. Okay, superscript represent the layer. Okay, its layer number. Okay, now we can see this already we have seen. So this is the transfer functions. Okay, transfer functions are nothing but multiplication of weights and input. So what are the weights? We are receiving the two inputs in this neuron. Okay, x1 and x2 and its weights we are multiplying with the weights. Okay, so this is the representation of transfer function. So this is the sigmoid activation function. Activations all functions also represented by the subscript and the superscript. Okay, this is the neuron number. Okay, this is the neuron number. This is the layer. Okay, this is the layer representation. So this is, we can say, by seeing this representation we can say, so this is the neuron. Okay, this is the hidden layer. Okay, this is the neuron of first neuron is the hidden layer. Okay, and we can say this is also okay, this is the our this is also hidden layer, first hidden layer and the first neurons. First neurons are transfer functions. Okay, so this way. So here this is the, and we can say this is the node. Okay, we can say this is the node. Okay, this is the node. Okay, this is the node. This is the edge. Okay, this is the edge. This is the edge. Okay, this is the edge. Okay, this is already we have seen. This is also two plan. Okay, this is where it starts. Okay, where it starts and where it is ends. Okay, which neuron it starts and which neuron its end. Okay, this is the output. Okay, this is the output layer. Already we have seen. Now we will see another representation of the cross entropy function. Here already we said. So this y cap is our real output. This is a1. Okay, this is the activation function of the our output layer. Okay, so output layer first neuron, because this is our real output here, real output y1. This is equal to y1. Okay, this is equal to y1. So we are simply here we can represent a1 0 or y1, both are same value. So here represent as a1 0. This way usually the neurons and its layers and its weights and the transfer functions are represents, okay, in the papers. Okay, next we will see, okay, next we will see uh, next we will see uh, next we will see so this is the general representation. Okay, this is nothing but, so already we have seen this is the generic, this is the generic representation. Okay, this is a generic representation. Already we have seen in the previous video, we have seen the first neuron and the hidden layer like that. So how can we represent in a generic way? Usually on this alpha represent the layer. Okay, this alpha represent the layer. Okay, this I represent the neuron. Okay, this I represent the neuron. So okay, already we have seen, already we told there is a weights are represented by a two part. Okay, two part. So this is the where it starts. Okay, where it starts, this is the previous start. Okay, starts from the previous layer. Okay, so this is represented alpha minus 1. Okay, if it is the particular layer, this weights belongs to particular layer, this weight is represented as the where it starts from. So the previous layer and the current layer where it belongs to the current layer. So this is represented as a alpha minus 1. Okay, this is represented as the alpha and alpha minus 1. This is the transfer function. Okay, this is the transfer function. Okay, so this is also same way. Okay, so already, because this is here, this is we have seen this is the input. Okay, this is the input. If it is the first hidden layer, this is input. Afterwards, this is the previous layers. Okay, previous layers output. Okay, we can say this is the previous layer output. We can represent this also as a Z or A. So if you using a linear transformation, so if you use a linear transformation, we can represent as a Z. So if you use any activation function, we can represent as a Z of I, alpha minus 1 and alpha minus 1. Okay, this is the A. This way we can represent. Okay, so this is the generic representation of any neurons output. Okay, any neurons output, we can simplify it as a sigma. Okay, further simplified as a, we can, this way we can represent. Okay, so, here, so this is the representation of, though this is the, this alpha representation any activation function. If you have any activation function, okay, though this is the function, any we can represent in this way any activation function. Then we will see already we have seen. So this is the our linear transformation. Okay, transformation matrix. So this, okay, already why we are using in this representation, because main reason is this linear transformation. The representation of linear transformation, we are using a row wise. Okay, a row wise linear transformation matrix. Okay, in the row wise linear transformation matrix, so the first, okay, this first neuron represent in a row wise. Okay, that only we are using this alpha weight equal to alpha and alpha minus 1. Then only we can make this arrangement is so easy. Here we can say w11, w12, w21, w22. In this way we can represent our transformation matrix. Okay, so for this purpose only we are using this alpha. In this way we are representing in the reverse way. Okay, the reverse way. Okay, so this is the output layer. Okay, this is the representation of the output layer transformation. Okay, so then, so all this we will see in our next video. We will see about that linear transformation and Jacobian matrix. Okay, this is about the network representation and notations. Okay, so we will see in our next video the linear transformation. Thank you.